Okay, everything in details now I am going to discuss. So, here I will discuss in details about the derivation of Fourier heat conduction, that means how this governing equation is coming, that related thing in details I am going to discuss now. Okay. Now, let us consider here a small element whose dimension is delta x, delta y, sorry, this is delta z and this is. So, let us consider a small element whose dimension in x, y, z direction are. Along x direction, let the elements have a dimension delta x, along z direction is dimension is delta z, and along y direction is dimension is delta y. This is the small element. In this small element, let us consider the first face of this small element have a distance along x direction, let us consider from here to here is x, and this is the dx, you can say delta x or dx. So, in this first face along x direction, what is the area of this first face, cross sectional area of this element? So, cross sectional area of this, you can say x directional face, that I am writing is Ax is equal to, you can write as delta y into delta z, this you can write. How it is coming? Generally the cross sectional area of Ax which is perpendicular, that area we should consider which is perpendicular to that axis. So, this axis x axis perpendicular area is Ax which is del y by del z. So, due to this heat conduction, how the heat is flowing at a distance x and at a distance x plus delta x, that first of all I will discuss. Let us consider heat is entering in this phase and it is coming out from the other phase. Okay. So, due to this, how the, because whatever the heat is entering, let us consider here heat flux I am representing, that is Qx, and let us consider in this phase the heat which is coming out, that I am representing is Qx plus delta x, in this way I am representing. So, the difference, whatever the heat is entering in left side phase and whatever the heat is coming out from the other side phase, the difference of these two generally will be stored due to the heat conduction along x axis. How it is coming, everything in details I will discuss. Okay. Now, so you know, first of all we will discuss what is Fourier heat conduction equation. You know this thing, Fourier heat conduction equation tells, I have already told you that heat flux whose unit is watt per meter square, this you can write as, is directly proportional to temperature difference between 2 point delta T, and it is inversely proportional to distance. If heat is conducting along x axis, then it will be delta x. Okay, that I have written. So, once we equate these things, this Q, this I am writing Q. So, this once you equate this thing, there is coming a constant K. This K is generally called as, thermal conductivity. This you should keep it in mind. Generally, one thing here you should keep it in mind, here this heat flux which is flowing over the medium, there is coming generally a negative sign here, always you should keep it in. Why this negative sign is coming? Because heat, whatever the temperature difference we consider, generally temperature, what we know, temperature difference should be generally temperature final minus temperature initial, this we should consider. That means temperature at final position minus temperature at initial position, that you can say. This is generally called temperature difference. This temperature difference generally always you should keep it in mind. This Tf heat is always flowing, you can say heat is always flowing from what? So, heat flow, here I am writing heat flow generally taken place from hot, medium or hotter position to cooler position, you can say hot position to, here I am writing, to cool position. This you should keep it in mind. So, here generally this T 0 is higher than T f. So, here generally T 0 should be higher than T f, but whatever the heat flux generally flowing, this is a positive value, this is a positive value, this is because heat is generally flowing along the positive x direction. So, this is a positive value. That is why what happens, to make Q as a positive quantity, this negative sign is coming, because this delta T is already negative. So, to make this negative things positive, another negative terms here we need to add, what I am telling, understand, or we need to put here another negative term, then generally this Q will become positive. This you should keep it in mind. So, here we can write heat transfer per unit area, or you can say heat flux flowing per unit area can be written as K into del T by del X. Okay. Now, these things once we convert to what is called in terms of joule, then what are the joule per unit area, then what are the things you need to do? You need to multiply, let us consider this heat is transferring at a particular time delta T, then you need to multiply with this thing Q into delta T. If you multiply, then this unit will become joule per meter square. This you should keep it in mind. So, let us, this I am representing in terms of capital Q x dot double dot, this way I am representing. So, this is the you can write, this is the heat flux flowing per unit area along x direction. So, what happens, let us consider these elements I have already shown at a distance x, this first phase is available and the second phase is at a distance x plus del x, this you can say. So, here in first phase, due to time delta T per unit area, how much heat is flowing, that I am just representing. Okay. So, in first phase at a distance q x, that means in first phase or left side phase, the heat flux which is entering in this element, this is generally you can say left phase heat conduction per unit area. This you should keep it in mind. Now, you know these things, this heat generally is flowing over a this left side phase, a cross sectional area is there. So, this cross sectional area if it will be there, then what should be the total heat. So, here I am writing the heat flow in this left side phase due to this total area will be generally this q double dot x into this A x terms will come. This much heat will be entering in left side phase. Now, what should be the heat generally coming out from the right side phase along x axis direction, that I am representing in terms of q x plus delta x. This you can generally write by using what? By using Taylor's series of expansion. What is Taylor's series of expansion? That little bit I am just discussing. Taylor series of expansion tell f of x plus you can say dx or delta x is equal to your f of x plus del by del x of f of x dx plus del 2 by del x square f of x dx whole square plus dot dot dot. So, here generally in this case we will consider these two terms only, higher order terms we will neglect. So, what should be this q double dot x plus dx? So, q double dot x plus dx you can write as here f of x plus del by del x, here I am writing f of x into dx, only these two terms I am considering. What is f of x here? So, f of x here actually q double dot x you can write, q double dot x, per unit area I am just discussing. So, plus del by del x q double dot x will be there, dx terms, higher order terms I am neglecting. So, what are the things we are getting here? So, here generally we are getting this equation. Okay. Now, this equation once you just put the this all terms, what are the things it is coming? So, you can write this will be generally minus k delta t by del x at a time delta t in joule per meter square I am writing plus del by del x I am putting this q double dot x value here, that is generally minus k delta t by del x, delta t is there into this dx terms is there, correct. So, let us consider this is equation number 1, this first equation, and let this is equation number 2. Now, so heat conduction in first or left side phase is represented in equation number 1. Now, heat generally coming out from this element from right side phase is this much. Then how much heat is stored in the body due to heat conduction per unit area along x direction, that I am going to represent. So, here I am writing. So, here the heat stored in time, the heat stored in time delta t per unit area, here I am till now I am not considering the AX area, per unit area due to heat conduction in x direction will be. So, heat stored in the body in time delta t per unit area will be how much? Q x double dot minus Q x plus delta x, because this left side heat is entering, right side heat is generally coming out, rest of the heat is generally stored. This if you will just do the calculation by using equation number 1 and 2, if you just minus it, then what are the things you will get? You will get generally you see here this minus and there is another minus is coming, this minus minus generally in equation 2 it will be plus. So, directly I am just putting it will be generally plus del by del x, okay, k delta t by del x del t time into delta x. This mass heat per unit area, you can say this is joule per meter square, this unit is joule per meter square. Due to heat conduction, this mass of heat is stored in this body. Okay. Now, what is the total heat generally stored in the body? due to this left side and right side face cross sectional area. So, that I am just writing. So, along x axis what are the area is there? So, along x axis the area is generally x. So, the total heat here I am writing. So, the total heat is stored in the body due to heat conduction in x direction. This will be what? This will be, you can write as, let us consider this I am representing in terms of q x total, this I am representing q x total. Okay. That means, along x direction what is the total heat, generally total heat is coming, that I am just representing q x total. Okay. So, this q x total will be, so what is the q x total will be, sorry, not this is the q x total. So, let this I am representing this q x double dot and these things, whatever the value we get, that is generally q double dot. So, the total heat stored in the body due to heat conduction in x direction will be equal to, let us consider this is equation 3, this equation 3. So, equation 3 into what are the things, it will be cross sectional area perpendicular to x axis, that is the thing should come. So, what are the things we will get? So, we will get generally here del y del x, this k generally if is constant in each direction, then generally we can consider k x is equal to k y is equal to k z equal to k. This is generally for isotopic types of material, isotopic types of material. If it is anisotropic, then generally this k x not equal to k y not equal to k z, this you should keep it in mind. So, here we generally consider, let us consider this is a isotopic material, because steel, aluminum, this metal generally considered as a isotopic material. That is why what happens, this k we consider as k x equal to k y equal to k z equal to k, thermal conductivity. Okay. This you can write what, del T by del x, delta T into delta x is there. With this once we multiply A x, what is A x? A x is the perpendicular area of x axis. That means, what is the perpendicular area? A x is equal to del y into del z. This is already I have written here. Okay. This you should keep it in mind. So, this is the total heat stored in the body due to heat conduction in x direction. So, similar way we can calculate what is the total heat stored due to heat conduction in y direction and z direction, similar way. So, here I am, instead of doing the same things again, here I am directly writing this thing. Similarly, heat stored due to heat flow by conduction along y and z direction, you can along y and z direction can be represented in equation what, let this is equation number 4, 5 and 6. What are the, what should be the heat stored due to heat flow along y axis, that can be represented as what is called del y here ky instead of ky here I am writing k del t by del y, and there will be generally delta y, and along y axis generally what should be the cross sectional area, y axis cross sectional area will be should be this. Okay. This area will be what? So, here generally dy dz dx. So, a y will be generally here dz into dx, this you should keep it in mind, and another delta t terms also will be there. So, let this is equation number 5. This is the heat conduction due to what? Along y axis heat stored in the body, and similarly along z direction heat conduction, heat stored will be in the body will be del by del z k delta t by del z delta t into here will be del z, and a z area will be generally you can say delta x delta y. From this element itself you can see, from this element what is the area along z axis, that is generally delta x into delta y, this you can see. So, what is the total heat stored in the body? So, total heat stored in the body will be generally total heat stored in the body due to heat conduction in x, y and z direction, due to heat conduction in x, y and z direction of the element will be how much? That will be generally equation number 4 plus that will be equal to generally equation number 4 plus equation number 5 plus equation number 6. These are the things generally we used to get. Now, this is due to the heat conduction, this you should keep it in mind. How the due to heat conduction, how the heat is stored in the body, that you can say. Apart from this thing, there can be some volumetric types of heat generation. These volumetric types of heat generation, how you can get? This heat generation generally is coming either from arc, if it is arc welding process, it can come from some frictional energy also, it due to some frictional force also it can come in case of friction stir welding. So, this volumetric heat generation generally let us consider I am representing due to arc welding is Q triple dot I am writing, which unit is watt per, let us consider meter cube. This is generally also called volumetric heat generation, or you can say this is generally called rate of volumetric, this unit will be watt per meter cube, or you can write as triple dot joule per second meter cube. So, this you can write this volumetric, this is actually so let us consider in this element this you can write this Q triple dot you can write as, if from the arc if this heat is coming. So, this volumetric heat flux intensity you can write as, generally there are different types of equation are there. So, this equation can be, this heat source equation can be a double ellipsoidal heat source, there can be some other heat source equation or there, in this equation form you can represent this heat generation equation. Okay. This is generally how per unit volume how much heat is generally coming from the arc per unit time, considering this is called volumetric heat generation, or you can say this is also called rate of heat generation per unit volume. volume. This rate of heat generation per unit volume with this, for this element what should be the total heat? For this element the total heat we can write as, so that things I am writing. So, if there is a heat generation rate per unit volume is Q triple dot, then we can write due to this what should be the total heat generation in this body. So, the total heat generation in the body will be you can say Q triple dot into body volume. What is the body volume? That is actually delta x delta y into delta z, okay. And for a small time delta t, if this heat is generating, then with this delta t terms you need to multiply. So, this is the total heat generation in the body. So, due to this heat conduction, whatever the heat is storing, similarly this much heat we are applying in the body. By use combination of these two effect, what happens? The body temperature generally rise, correct. This whatever the small element is there, this small element body temperature is generally rise. So, for these things we can represent whatever the heat stored in the body will be generally utilized to increasing the temperature. So, how much increasing the temperature is there, that we can represent by combination of these two heat input. One is from the volumetric heat source, another one is from the what is called heat conduction along three perpendicular direction and along all three direction. So, generally that I am writing. So, temperature of the body generally will rise. So, this temperature rise can be represented. So, rise of temperature due to what? Due to heat conduction as well as due to this rate heat generation will be equal to, you can say, mass of the body into a specific heat, especially a specific heat of the body at constant temperature, or a specific heat of the material, you can say whatever the material is there, into a rise of temperature of the body. So, that I am rise of temperature of the body, this I am writing. So, mass of the body of this small element, what we can write? Density into volume of this small element, volume is dx dy into dz. Let us consider a specific heat is C. Generally here a specific heat we consider, that is generally a specific heat at constant pressure. So, here this I am writing here C into rise of temperature is, let us consider delta T. This way you can write. Now, this is equation number 7, this I am writing equation number 7. Now, what happens? Equating general equation number 4, 5, whatever the 6 equation we get with this equation number 7, what we get? So, this we are writing. So, equating equation number, this is equation number 6, this is equation number 7, and this is equation number, let us consider 8. Okay. So, equating all this equation, what we are getting? So, equating equation 4 plus 5 plus 6 plus 7 with equation what? With equation number 8, what we get? That is actually our you can say Fourier tangent heat conduction equation. What we will get, that I am going to write. This will give you a equation del by del x k del t by del x plus del by del y k del t by del y plus del by del z k del t by del z over these three terms. There is a common term, that is generally you can say del x, del y, del z into del t. You can see in previous slide it is already there, del x, del y, del z and to del z is there, plus another terms is there, that is equation number 7, that is q triple dot into delta x, delta y, delta z into delta t. This term also is there. This is this equation also is also there. This should be equal to with equation 8, that is actually you can say rho into volume delta x, delta y, delta z into a specific heat into rise of temperature delta t, into rise of temperature delta t. So, what you can see from this equation, there is a common terms delta x, delta y, delta z. You can say there is a common term delta x, delta y, delta z are there. So, we can eliminate both sides of these terms. So, what are the things finally we will get, and we generally consider, let us consider this isotopic material. So, I am taking k outside. So, what are the things we will get? So, k into I am taking k outside, because this k is constant in all three directions, that is why I am taking this one outside. So, you can write del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square, okay, into delta t. This should be plus q triple dot into delta t is there, and the right side will be rho c into temperature difference, correct, rho c into temperature difference. Now, this equation further you can write as del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square plus q triple dot by k is equal to rho c by k del t by del time. Okay. This is generally called t dot. So, this equation is known as, let us consider this is equation number 9. This equation number known as Fourier tangent heat conduction equation. This equation is known as Fourier tangent heat conduction equation. Okay. This equation generally is used for finding out different solution of what is called welding heat transfer. Now, what this equation generally we use for different solution of welding related analysis. Now, how it is coming, this in details here I am differential form I am showing. This thing already I have shown in second slide, you can say there I have also shown this similar types of one equation that you can remember. There I have shown that equation, that I am just going to write that equation in differential form, like rho c t dot, you see there we have written these things, rho c t dot minus grad into k grad t. This you can see, this grad into grad t generally is giving this first three term if k is coming out, because grad grad T generally give this first 3 terms, this you should keep if k is constant. So, that is why I have written like this, okay, minus another q triple dot terms also there, that is generally watt per I have already shown meter cube, that is heat generation rate per unit volume equal to 0. This equation already I have shown in you can say second or third slide. Okay. So, this derivation part now I am representing in details in this case. Now, this equation generally we use as a governing equation for what is called any types of heat conduction or heat transfer analysis. So, what are the main or important things from here you are getting, that related things little bit I am just explaining, then it will be further more clear to you. Generally these things also sometimes represented as del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square plus q triple dot by k 1 by alpha del t by del t. What is this alpha called? This alpha called thermal diffusivity, this you should keep it in mind. Thermal diffusivity. Thermal diffusivity, what is the significance of this thermal diffusivity? What you can write? Thermal diffusivity means heat conducted divided by heat stored. This ratio, because what happens, this thermal diffusivity is actually what? K by rho c. Okay. This K by rho c generally called heat conducted by heat stored. What is the significance of this diffusivity? So, always you should keep it in mind. It generally gives the measure of, you can say it generally gives the measures of how quickly the temperature will change when it heated or cool. This you should keep it in mind. That means, when when a body is heated or cool, how quickly the temperature is rising or temperature is decreasing, how quickly, that things generally define this thermal diffusivity. Always you should keep it in mind. If in a body, if this thermal diffusivity is high, if alpha is high, then that body's temperature will rise rapidly, as well as it will cool also rapidly. That means, its cooling and heating will rate will be higher. This you should keep it in mind. That means, if in a body this alpha is higher side, then the body will be heating quickly, as well as during cooling it also cool rapidly. This you should keep it in mind. Okay. Now, how this thing is coming little bit you can see from here, because this equation also have a name. This equation, let us equation 10, this equation also have a name, this equation also called governing equation of, this equation also called, you can say governing equation for transient heat transfer analysis. Okay. This was developed by Fourier, that is why this equation name also calls Fourier transient heat conduction equation. Based on this governing equation, generally we used to find out the temperature distribution of a body. What should be the temperature distribution of a body if this body is subjected to some heat input or heat generation, then what should be the temperature rise of this body, that things we can easily find out. So, for finding out this temperature T, this equation you need to solve. For solving this equation, what are the input parameters required? Like what happens for solving the, for finding out the T, what are the things required? This, what are the other parameters are there? Other parameters are density, specific heat, thermal conductivity, these are the 3 parameters are there. Apart from this thing, there is a terms temperature also, time is also there. there is another parameter, that is time is also there. So, this time generally depends on welding velocity, you can write welding velocity, and these are all material constants. So, to find out the temperature distribution over the plate during welding, what are the input parameter required? First of all, the input parameter required are what material we are using, in which material we are doing the welding actually, that material density we need to know, specific heat we need to know, thermal conductivity we need to know. These things can be temperature dependent, or this thing can be a constant property. Generally these things is if you use temperature dependent material property, that will give you more accurate result during your calculation. If you use constant material property, then that also give you some temperature history over the entire welded joints as well as plate, but what happens that that can be little bit erroneous if you will constant material property. And Q, this Q generally is depends on arc energy, how this arc energy as well as arc heat source shape and its size, it generally depends on this. How this Q generally calculate? This Q is a function of, you can say, is a function of coordinate system as well as voltage, current, it is also depend, as well as its efficiency also. This you should keep it in mind. So, from the governing equation itself, you can get the information what are the input parameter required to find out the output, like temperature history or temperature distribution T over the welded plate. From this equation itself you can get the idea. So, always you should keep it in mind. For solving any types of thermal analysis or structural analysis, first and foremost things you need to know, that is what is the governing equation you need to use. So, based on this governing equation you need to decide what should be your input parameters on the, because how you can decide that input parameter, because to see that governing equation itself you will get the information what is your input and what is your output. This you should keep it in mind. Okay. So, in next lecture I will discuss in details what are different solution of this Fourier transient heat conduction equation, that I will discuss like what happens if in a body, if you will apply a stationary point heat, then what should be the thermal history over the entire plate. If in a plate, if you use a line heat source instantaneously, then what should be the temperature history of the entire plate. As well as I will also discuss if the body is subjected to moving heat source, then due to this moving point heat source, how the temperature history will be coming, that solution I will show. For a line moving heat source, how the temperature history will come, that also I will show. So, in details in next lecture I will discuss solution of this governing equation for different heat source condition. Okay. To this next class I will start from here.